Physics Class 11, Chapter 7, Systems of Particles and Rotational Motion. In the last class, we have studied radius of gyration and theorems of perpendicular and parallel axes. Today we shall study kinematics of rotational motion. It is a branch of mechanics concerned with objects in motion but not with forces involved. So this kinematic of rotational motion, the kinematic, that is the branch of mechanics which is concerned with the objects in motion but not with the force involved by the motion is there. Okay, so the force involved, they are not concerned, but only the objects which are in motion. So that comes under kinematics. The kinematic equations in rotational motion, angular displacement theta, angular velocity omega and angular acceleration alpha are analogous to kinematic quantities in linear motion, displacement x, velocity v and acceleration a. Now in linear motion, displacement is x, velocity is v and acceleration is a. Similarly, in rotational motion, the quantities, this angular displacement is theta, angular velocity is omega and angular acceleration is alpha. So they are analog to, one is in a rotational motion, other one is a linear motion. The kinematic equations of linear motion with uniform acceleration. So we have studied these kinematic equations of linear motion with constant or uniform acceleration. We have studied the three equations. First one is v is equal to v naught plus at, x is equal to x naught plus v naught t plus 1 by 2 at square, and v square equal to v naught square plus 2ax, where x naught is initial displacement, v naught is initial velocity. Okay, so we have studied these equations where x naught is initial displacement and v naught is initial velocity. Okay, these are the kinematic equations of linear motion when acceleration is constant or uniform. The corresponding kinematic equations for rotational motion with uniform angular accelerations are omega is equal to omega naught plus alpha t, theta is equal to theta naught plus omega naught t plus 1 by 2 alpha t square, and omega square is equal to omega naught square plus 2 alpha theta minus theta naught. So similarly, kinematic equations for rotational motions with uniform angular accelerations are, these are the three equations. Okay, they are similar to the equation which we studied in the kinematic equation of the linear motion. Okay, and these are kinematic equations in rotational motion. Okay, where theta naught is initial angular displacement of the rotational body, rotating body, and omega naught is the initial angular velocity of the rotating body. Okay, and these are the equation. Now we shall derive these kinematic equations of rotational motions. Example 7.13. Obtain the kinematic equations of rotational motion from first principle. So we have to derive the kinematic equations for rotational motion. Okay, so these three equations we have to derive. So first, the angular acceleration is uniform. Okay, in this we consider that angular acceleration has to be uniform, constant. Okay, that means d omega by dt is equal to alpha, constant. So d omega by dt equal to alpha. Change in the angular velocity will give you angular acceleration. Dt transfer over here, so you get d omega is equal to alpha dt. Integrating on both the sides. So integral for this integral omega naught to omega, d omega equal to alpha is a constant, integral 0 to t dt. Okay, omega naught is the initial angular velocity and omega is final. Okay, 0 is the time at t equal to 0 time and t equal to t time, this is time t. Okay, now we use the formula integral a to b dx equal to, if it is with respect to x, here nothing is there means 1 is there, so the integral of 1 will be with respect to x is x, lower limit is a to b, and when you apply the limit b, first you have to apply the upper limit minus the lower limit, so it will come b minus a. Okay, so integral a to b dx equal to x from a to b, apply the upper limit minus the lower limit, so b minus a. Instead of x you have to put the upper limit and the lower limit. So for this it is with respect to omega, so answer is omega, and the lower limit is omega naught, upper limit is omega, equal to alpha. Here also 1 dt, so with respect to t the integral will be t, limit is 0 to t. Apply the upper limit first, so omega minus omega naught equal to alpha t minus 0. So this gives you omega equal to, if omega naught if you transfer over here it becomes plus omega naught, and here plus at. Okay, plus alpha t, so plus alpha t, and this is the first equation. Okay, the first equation of the kinematic equation of rotational motion omega is equal to omega naught plus alpha t. Again, omega is equal to d theta by dt. Okay, change in displacement, angular displacement will give you angular velocity. So omega is equal to d theta by dt. Now omega value we can place from equation 1. Okay, from equation 1 value of omega. So I put the omega value from here, omega naught plus alpha t equal to this one, d theta by dt. Now I'll transfer dt over here, so you get here omega naught plus alpha t into dt equal to d theta this side. Now integrating on both the sides, so integrating this from 0 to t, and this will be theta naught to theta, initial displacement and final displacement. Okay, so integral 0 to t omega naught plus alpha t dt equal to integral theta naught to theta d theta. Omega naught is a constant, but there is integral dt, right? This dt you can give to here also. So omega naught integral dt plus alpha integral t dt. So for this integral will be omega naught t. Okay, 1 into dt, so it is t plus alpha and here t. So we use the formula integral x power n dx equal to x power n plus 1 by n plus 1. Okay, so here t power 1. So here t power 1 means 1 plus 1, that is 2 divided by 1 plus 1, that is 2. Okay, so here we get t square by 2 alpha as it is. Limit from 0 to t equal to, now this just like the previous one, integral ab dx with respect to x, answer is x, and a to b. Okay, apply the upper and the lower limit. So here 1 d theta with respect to theta, so the integral of 1 will be theta, theta naught to theta. Apply the limit, so when you apply 0 it will be cancelled, right? So only apply the t. So here omega naught t plus this 2 is there, I am writing as 1 by 2 alpha t square. Okay, t is there, so t square, right, equal to upper limit theta minus the lower limit theta naught. Now this implies if you transfer theta naught here, here you get theta equal to this negative and transfer becomes positive theta naught plus omega naught t plus 1 by 2 alpha t square. Okay, this is the second equation, this one. Now next we know that alpha is equal to d omega by dt. Change in angular velocity will give you acceleration, angular acceleration. Now I multiply and divide by d theta. Okay, so d omega by d theta into d theta by dt. This d omega and dt is here, d omega d by dt. Okay, and d theta I am multiplying and dividing. Now d omega by d theta as it is, but d theta by dt is nothing but omega. Okay, d theta by dt is equal to omega. So you know that is the formula. So you can put this value d theta by dt as omega. I have put d theta by dt equal to omega, angular velocity. Okay, we know that part. Now d theta transfer here, so alpha into d theta equal to here omega into d theta. D omega. Okay. Now integrating both the sides, so alpha is a constant, out of the integral d theta theta naught to theta. Okay, d theta theta naught to theta equal to integral omega naught to omega, omega d omega. Okay, this is with respect to theta, this is with respect to omega. So when you integrate 1 with respect to theta, it is answer is theta, and limit is theta naught to theta, this alpha as it is, equal to here omega, so omega power 1. You have to use this formula, integral x power n dx equal to x power n plus 1 divided by n plus 1. Here omega power 1, so you get omega power 1 plus 1, that is omega power 2 divided by 1 plus 1, that is 2, and the limit is omega naught to omega. Apply the limit, so equal implies alpha theta minus theta naught. Okay, equal to this 1 by 2 I am just taking out of the bracket, so 1 by 2 here omega square, first the upper limit minus omega naught square, the lower limit. Okay, 2 transfer over here, so we get here 2 alpha theta minus theta naught equal to here omega square minus omega naught square. Minus omega naught square transfer over here, so it becomes positive, and here you get omega square equal to omega naught square plus 2 alpha theta minus theta naught. Okay, so that is the third equation, this equation. Okay, so we have found all the three equations of kinematic equation, all the three kinematic equation of rotational motion. So that is solution of example 7.13. Example number 7.14. The angular speed of a motor wheel is increased from 1200 rpm to 3120 rpm in 16 seconds. Number 1. What is its angular acceleration, assuming the acceleration to be uniform? Number 2. How many revolutions does the engine make during this time? Here they have given us the angular speed in RPM. RPM means revolution per minute. So first we shall convert it into radian per second. So for the first part, the initial angular velocity omega naught equal to 1200 revolution per minute given, okay, and I'll convert into radian per second. So I'll multiply by 2 pi and divide by 60 second per minute, okay. So multiply by 2 pi and this value and divide by 60. So when you simplify, you get 40 radian per second, okay. To convert into radian per second revolution per minute, you have to convert in multiply by 2 pi and divide by 60. Okay, and the final velocity, angular velocity omega is equal to 3120 revolution per minute. Okay, RPM is revolution per minute, convert into radian per second. So multiply by 2 pi and divide this value by 60, 3120. Okay, 2 pi 3120 divided by 60. Okay, simplify, you get 104 pi radian per second. Now from equation 1 of kinematic equations, kinematic equation of rotational motion. Okay, equation 1, that is this one. Okay, this one, omega is equal to omega naught plus alpha t, or from here we can say omega is equal to omega naught plus alpha t. So I use this equation number 1. So you write omega is equal to omega naught plus alpha t. Omega value, the final angular velocity is 104 pi, equal to omega naught is the initial velocity, initial angular velocity 4 pi. So put here 4 pi. Okay, this 4 pi radian per second, and this one 104 pi. Plus alpha we have to find into t, time they have given us 16 seconds. Okay, so put t equal to 16. Now 40 pi transfer, so 104 pi minus 40 pi equal to alpha into 16. This simplification is 64 pi, and this 16 if you transfer over here, it will go in the denominator. So you get, if you simplify this, you get the alpha value as 4 pi. Now this is angular acceleration, so the formula will the unit is radian per second square. So alpha equal to 4 pi radian per second square. So that is the first part. They have asked us to find the angular acceleration. For the second part, the angular displacement in time t is theta equal to omega naught t plus 1 by 2 alpha t square. Okay, so we are using the formula, this one, theta equal to theta naught plus omega naught t plus 1 by 2 alpha t square. Okay, and theta naught initially we consider that it is at the 0 point. Okay, displacement is 0. So I use the second equation, that is theta is equal to omega naught t plus 1 by 2 alpha t square. Okay, and here also we have derived the same equation, theta is equal to theta naught plus omega naught t plus 1 by 2 alpha t square. But here we consider that initial displacement is 0, starting from 0. Okay, so theta naught is not written here. Now omega naught value, we know that it is initially the velocity is 40, so 40 pi into time t 16 plus 1 by 2 as it is, and alpha we found here 4 pi. Okay, so I put here 4 pi. Okay, alpha value, and t square is 16 square, so 16 into 16. Right, now this one is, if you multiply, you get this as a 640 pi, and if you simplify this part, okay, altogether, then you get here 512 pi. Here there is a plus, so this value is 640 pi plus 512 pi. Sum up together, you get 1152 pi. So 1152 pi. This is in this one, we have displacement, we have to consider now in a revolution. Okay, so number of revolution, you have to just divide this value by 2 pi to get the number of revolution. So number of revolution equal to 1152 pi divided by 2 pi, because in one revolution it is cutting the distance 2 pi, or the angle which it is making is 2 pi angle. Okay, in one revolution it makes angle 2 pi in one full revolution. So you have to divide 11252 pi divided by 2 pi. Okay, 1152 pi divided by 2 pi cut, divide this by 2, so you get 576. Right, so we have found the answer as, the first answer is angular acceleration is 4 pi and the number of revolution is 576. So conclusion, we can say that therefore the angular acceleration of engine equal to 4 pi radian per second square, and number of revolution in time t equal to 16 seconds is 576. Okay, this value. So that is solution for example 7.14. We'll keep this much for today. Thank you very much.